Good evening, everyone. Welcome to Observatory Nights. My name is Christine Pulliam, and I'll be your host. Tonight, we are talking about nothing less than the birth of the universe. The question, where did we come from, is one of the most fundamental questions that we can ask. And it's only in the past few decades that we've begun to be able to answer that question. Our first clue was when we found that galaxies all around us are rushing apart from each other in all directions. If you rewind that, run it in reverse, that suggests that everything had a beginning in time and basically exploded outwards after that. There was a cosmic explosion that we call the Big Bang. And the Big Bang, contrary to common conception, didn't just spew matter into space. The Big Bang was an explosion of space itself. In fact, the Big Bang was so energetic that it created this hot glow that still remains all around us today, even now, 14 billion years later. Scientists discovered that glow, called the cosmic microwave background, back in 1965. And ever since, they have been studying it, trying to tease out the secrets about the very birth of our universe. Tonight's speaker, John Kovac, is an associate professor of astronomy at Harvard and leader of the BICEP2 collaboration. John has devoted his career to measuring the cosmic microwave background with exquisite precision. To do that, he has traveled to the South Pole more than 20 times and faced some of the harshest observing conditions on this planet. Tonight, he is going to tell us why the heck he would do that and tell us all about his quest to understand the beginning of the universe. Please help me welcome John Kovac.
Thank you. Thank you very much. Thank you for that very kind introduction, Christine. And it's a real honor to be here tonight to do an observatory night here at our own CFA. And I want to thank all of you for coming. It's wonderful to see such a broad and diverse audience, see so many people turn out tonight. I'm going to be speaking tonight about the oldest light in the universe, as Christine said. And I'm going to be talking about these very extraordinary telescopes, many of which are at the bottom of the Earth, that are custom designed to observe this oldest light. And I'm going to have a lot of slides, and many of them will have plots and graphs and data, and one of them will even have equations. As a warm-up and as a thank you for all coming out tonight, I wanted to start off the evening by showing you something that that I think is exquisitely beautiful and that very few people actually get a chance to see firsthand. So this is what the South Pole looks like by daylight. This is actually pretty close to how it looks right now because the sun came up at the South Pole just under a month ago. And it will stay up for another 5 months before it disappears below the horizon for 6 months of darkness. And here on the horizon at the South Pole, you can see what a barren wasteland it is for the most part, but this is the view that you get as you walk out from the main station, the kilometer or so past the actual geographic South Pole, to the observatory facilities, and you see the array of telescopes that have been built up over the last 2 decades down there at the South Pole to observe the cosmic microwave background, the radiation I'll tell you about tonight. But this is the view that most of us get when we work in Antarctica because we only ever see it in the daytime. And then most people get on a plane at the end of the summer season, which happens in February, as the temperatures drop too low for the planes to fly. And then it gets colder and darker, and a few brave souls stay behind. And
where our experiments are.
Let's see if we can mute that sound, please.
The team used 2 telescopes.
So a few brave souls will stay behind at night, and then they get this extraordinary view, this view that few people get to experience firsthand. So temperatures can drop to minus 100 Fahrenheit or below. The air, the coldest on Earth, is also the driest. So it's nearly transparent to the microwave light that reaches us from the universe, from the early universe that our telescopes are measuring. So in these sped up videos, you can see overhead the aurora, which our telescopes don't see. And you can see the galaxy turning like a pinwheel about a fixed point directly at zenith, directly above you. That means that you are really at the South Pole. You can see it up there at the top, the point about which everything is rotating. And that means that bits of the sky that our telescopes observe, including, you can see here, these are the Magellantic Clouds here, these cotton balls. Everything stays above the horizon 24 hours a day and just rotates. And our telescope, the BICEP 3 telescope, that the Winter Rover observer who took this video just a couple of months ago before the sun came up, is in this enclosure here, scanning back and forth, measuring that earliest light that comes to us from shortly after the Big Bang. And he's been working very hard, so he'll be very happy to see the first planes arrive at South Pole later this week. And I'm going to be going down there myself. In about 2.5 weeks, I'll be leaving, actually, to go help relieve Sam. He's done a great job, and through that 9-month period, he's been working so hard because he hopes that the data that he's been taking with this telescope, BICEP 3 in this case, is going to tell us something that we didn't know before about the very first instance of the history of the universe. So where we are in modern cosmology right now is that we actually think we've got a very comprehensive picture of most of the history of the universe. And that's an extraordinary statement. It certainly wasn't true not long ago. So when we look out at the present-day universe around us, we see familiar stars and galaxies, and we understand how those evolved over the last 13.7 billion years from the first stars that emerged a few 100 million years after the Big Bang. And in fact, the light that we study with our telescopes gives us a snapshot of the universe at a much earlier time, about 380,000 years after the Big Bang. I'll be talking a lot more about that. We know more about the universe probably in that period than we even do about the present-day universe. We have such high precision data on what the universe looked like at that early time. And we can even read out hints in that map of the initial conditions of what happened earlier on. So that's going to be the theme of my talk, how modern cosmology fits together beautifully and yet leaves these very big open questions, these frontiers that we can push on. And that's what characterizes the field right now, an opportunity to study these open mysteries. But first I want to back up again and just emphasize the story that Christine already told, the history of modern cosmology. And it's worth emphasizing in this year, 2015, that we're celebrating a couple of really important anniversaries. So first of all, modern cosmology was really born 100 years ago this year, and it was born with Albert Einstein's general theory of relativity. So that theory told us that space is curved by gravity, and even Einstein himself didn't initially feel very comfortable with the cosmological implications of his own theory. But the upshot was that general relativity implies that the universe itself is dynamic, that space can expand or contract. And in fact, it naturally does. It's very difficult to prevent it from doing that. And it took others in the 1920s, Georges Lemaitre, notable among them, and evidence taken by observers like Edwin Hubble here, to really piece together this picture that actually we do live in a universe that's expanding. When we look at galaxies, we see them rushing apart in all directions. Space appears to be expanding. And so if you run that backwards in time, one way of interpreting that expansion, at least, and it wasn't obvious to everybody that this was the only way or even the right way, is that there was a time when everything was much closer together, and therefore the universe was much denser and probably much hotter, like the inside of the sun. And so some brave souls worked out in the 1940s and beyond how you could, in such a hot, dense early universe, cook up, through nuclear reactions, the light elements that we see that stars are mostly made of. And so this looked plausible, but it really wasn't until the realization that came out of this period, and it took another 20 years before people put the pieces together and understood that that hot, dense beginning meant that we could still see that glow. We could go and look for it. And that theoretical realization actually came along at almost exactly the same time that this radiation was discovered. So what is this glow that I'm talking about that we're looking for? Well, the cosmic microwave background is the light that you see when you look out as far as you can. You look as far as you can with your telescope, you're looking back in time. You look across 14 billion light years of radius, 14 billion years of the history of the universe. And then all around us, we will see the universe at that distance when it was in its infancy, hot and dense. And when it's at a certain temperature in the early universe, the gas of the universe itself, the hydrogen, the helium that makes up most of the universe, is hot enough that it actually is ionized. It forms a plasma. And that's really important because a plasma, an ionized plasma, where you don't have neutral atoms, you have charged particles, is very effective at scattering light. Light will just bounce around. So light that was probably at equilibrium with that plasma at early times has been just bouncing around through that early history of the universe. And I'm running now the clock forwards in time from the early history of the universe up until a point when that expansion has cooled the universe so that that plasma condenses, undergoes a phase transition, and neutral atoms form, neutral hydrogen forms. Suddenly it becomes transparent, and light can free stream on average the distance of the universe. And that light, these photons that were released at that surface of last scattering, when the universe underwent this transition, and it happened relatively suddenly, 380,000 years or so after the Big Bang we now know, gives us a snapshot of what the universe looked like at that time. And that light has come to us mostly undisturbed in straight lines, more or less, as we'll see later, since that time. So this is the cosmic microwave background, and it was first detected 50 years ago today, and that's the other big anniversary that we celebrate. So this is Bob Wilson and Arno Penzias. Bob Wilson is here at CFA, and is a perfectly wonderful, charming guy. His office happens to be next to mine, so I'm very fortunate. So in 1965, they used this horn antenna at Bell Labs to discover the microwave background. They received the Nobel Prize for that in 1978. More importantly, this was really the really launched observational cosmology as a credible science because it convinced everybody that the Big Bang was for real. This was the smoking gun evidence that the universe had a history, it had an origin in a hot Big Bang. Okay, fast forward through many, many years of hard, careful follow-up measurements of that radiation. 35 years after its discovery, that radiation was measured in enough detail to reveal faint ripples, ripples that are no stronger than a few tens of millionths of a degree of temperature variation in radiation that we typically characterize as being 3 degrees above absolute zero in its absolute effective temperature. So 3 degrees is already a very faint radiation, much fainter than radiation coming from anybody in this room. And we're measuring variations in that radiation now that is at the tens of millionths of a degree level, and making maps that you see with the instruments up here, balloons and ground-based telescopes, some of them at the South Pole, telescopes like the WMAP satellite that are orbiting the Earth are mapping out this radiation in enough detail that we can actually look at the statistics of these faint ripples, these fluctuations, and plot them as a function of how big they are on the sky, as a function of angular scale. So this is one of 2 kinds of graphs that I'm going to be showing tonight. So this is an angular power spectrum. And what it shows is how strong are the ripples in these maps that we might make across the whole sky at different angular scales. And scales of about 1 degree on the sky are right here. So Christine just said that the full moon is half a degree. So that would be, if I take that and I double it on this axis, so half a degree is here. Okay. And what you see is that there are certain scales at which these ripples that we see in the CMB, the microwave radiation, are much brighter. And those reveal sound waves that are passing through the plasma of the first 380,000 years. These sound waves are predicted to be there very firmly by our theory of how physics happens in that early plasma, just assuming that the density fluctuations in the early universe, which are very faint, were all kicked off initially in phase at the very beginning, all together at the start of the hot Big Bang. And that's very important. There's an assumption of initial conditions there. If they're all launched together at the same time, then you get this very coherent-looking spectrum of a primary tone and overtones that are harmonics of that. And then the amplitude of these different peaks, the primary peak and its overtones, can tell you what's in that plasma. They tell you its constituents. So the data that are coming from these maps are plotted here as the points on this graph. And the red line is a theoretical fit that has only 6 parameters in it. And that tells us what is the composition of the universe in terms of dark matter, ordinary matter, dark energy. It tells us what is the strength of that initial spectrum of perturbations, fluctuations that were kicked off at the Big Bang, and how flat is that spectrum? How tilted is it? How much stronger are the initial perturbations at large angular scales compared to small ones? The parameters that you can read out of a model fit like this to the data can be plotted on the second kind of graph that I'm going to be showing tonight, different examples of. So this is a parameter constraint plot. Okay, so the data that I just showed you is an example of CMB data, cosmic microwave background data, that can constrain model parameters, and in this case, the model parameters that I'm plotting in the standard Big Bang model tell us omega lambda. Okay, does anyone know what omega lambda is? I see a few people nodding, but most people not. That's the amount of dark energy in this model. So you dial this up, more dark energy, dial it down, less dark energy, and omega matter is the amount of ordinary matter in this model. And if you add those things up to equal 1, you get a universe that's geometrically flat in these units. That's the critical density. So you can get there by adding more matter and less dark energy, or more dark energy and less matter. And the CMB can constrain very precisely a particular combination of those parameters. But there's a degeneracy. It can't constrain very well, can't distinguish between parameters that lie along this line. And so the data constraint is depicted as these ellipses. The goal of making better measurements is to have those ellipses shrink and shrink until you zero in on a point in parameter space that tells you what are the values of these numbers that really describe our universe. But you can see here that the CMB data that's being used in this plot is good at constraining only a particular combination of these parameters. But other kinds of cosmological data sets can constrain different combinations. So supernovae data is shown in this ellipse here. They constrain a different combination of these same 2 parameters. Galaxy surveys made by some other people, including some here at CFA, constrain this ellipse. And the really cool thing about this is that these 3 ellipses, they don't have to overlap at the same point, but they all do. Different kinds of evidence all line up with a concordance picture of the standard model of cosmology right there, and it happens to lie right on this theoretical line that says that we live in a flat universe, and that's pretty cool. So we have a picture of the standard model of cosmology that fits together very nicely. Okay, the CMB results, and here I've intentionally picked an old version of this cosmic pizza plot that many of you may have seen different versions of now. This is one that's almost 15 years old, but it was produced from early maps of the cosmic microwave background before we even had the satellite, the beautiful satellite data, some of which I just showed. And this tells us what the universe's makeup is. So around 4% ordinary matter, around 30% dark matter, around 65% dark energy. These numbers have changed by a few percent over the last 15 years, but the story hasn't. The standard model has really held up as we've thrown more and more precise data at it over the last 15 years. And this is a very strange brew. We've also learned the universe is flat and is smooth to very high precision. And this is consistent with a theory of initial conditions that I'm going to be talking a lot about tonight called inflation. And a question I'm going to raise is, can inflation explain also where that those initial density fluctuations come from. Okay, so to set the stage for that, I'm going to talk a minute about things that this concordance cosmology, the standard picture of the Big Bang that we have, don't explain. It leaves as open questions. And these are all questions of initial conditions. So we live in a universe that is apparently very smooth on its largest scales. And we can tell this, for example, by measuring the temperature of the cosmic microwave background in different spots on the sky. In fact, we can look in opposite directions. And when we look out 14 billion light years that way and 14 billion light years that way, we're observing different points of the early universe that haven't exchanged light since that time. Those different regions of the very early universe, through the conventional expansion history of the universe, would have had no way of exchanging information or of figuring out what temperature they ought to be. And yet when we do that observation, we look and measure their temperature, they're the same temperature to 5 decimal places, to exquisite precision. So how could the universe have started off looking so much the same everywhere? How could it be so smooth? And indeed, how could it be as flat as it is? So general relativity tells us that space can be bent. Gravity bends it, and it will be bent normally by its expansion and by the density of energy and matter that's in it. But in an expanding universe, any departure from geometric flatness on large scales, so if triangles have angles that don't add up to 180 degrees, any departure from flatness will get amplified as the universe expands. And we know from our observations that the universe started off much, much smaller than it is now, much smaller indeed. So when we look out and see the universe looks flat on the largest scales we can measure now, that means that it must have been exquisitely flat in the past. It's almost as though we've discovered a pencil standing on its tip, and it's been standing on its tip for 14 billion years. It's unstable. And so we wonder, how could it have been tuned to be so exquisitely flat at very early times that it still looks flat today after all that expansion? We also don't see any exotic high-energy physics relics, any relics from grand unified theories, from symmetry breaking in the very high-energy universe that would have occurred if the hot Big Bang just naturally plays back to the highest energies where the forces of nature are unified. We don't see things like magnetic monopoles, and that's a mystery for high-energy physicists. And the standard Big Bang picture also doesn't tell us how structure arose in the early universe. It leaves that question unaddressed. And so this theory of inflation seeks to answer those questions by saying that in the first tiny fraction of a second, the universe underwent a different kind of expansion, exponential expansion, expansion that had a specific doubling time, as exponential growth does. And so the universe doubled in size, doubled in size, doubled in size again in tiny fractions of a second, until it grew at a mind-bogglingly fast rate. So that extremely rapid exponential expansion has the ability to, because it's so much faster than regular expansion, has the ability to take a universe that starts off very small, smaller than an atomic nucleus, and stretches it out to much larger scales so that it could start off in equilibrium and grow to an extremely large size and then look smooth at much later times as we begin to observe progressively larger and larger scales through the normal expansion history of the standard model. The exponential expansion also has a dilution of curvature, stretches out space so rapidly that any ripples, any departures from flatness get stretched, and the universe becomes exquisitely flat through that exponential expansion. Any exotic high-energy particles that existed before inflation started would get diluted to a mind-bogglingly small density, so that in the entire observable universe today, you might have only one magnetic monopole, say, and we haven't been lucky enough to observe it. So it can solve many of those early conceptual questions that people had about the initial conditions of the standard model. But it also has the potential to explain where the fluctuations that we see in the early universe, from which all subsequent structure, galaxies, stars, planets, ultimately us, evolved through gravitational collapse. And how does it do that? Well, I'm going to take a quick stab at explaining this, and I'll warn you that it's a difficult concept. It's a complicated one. And you can tell that by recognizing who's up here in the corner of this slide. I'm sure that everybody here has heard of Stephen Hawking, and I'm guessing that some of you may also have heard of something called Hawking radiation. So Stephen Hawking, very boldly, in the mid-1970s, studied the action of quantum mechanics in the very strong gravitational regime that happens near the event horizon of a black hole. And this was brave because quantum mechanics and general relativity normally don't play well together. It's one of the holy grails of modern physics to try to come up with a quantum theory of gravity. But Hawking was able to determine that quantum fluctuations, which normally fill all of space-time and are depicted here as virtual particles springing into existence and then annihilating each other. This happens all around us, effectively. The laws of quantum mechanics, the uncertainty principle says this is happening everywhere, but we don't normally observe these particles except indirectly. They govern the forces of nature, the laws of physics as we know them. And this is how quantum mechanics gives us a picture of how those forces operate. But these particles themselves aren't individually observable except if they happen near the event horizon of a black hole, which you may know is the point of no return. So if you go over the event horizon of a black hole, there's no escape from the strong gravity of a black hole. And if you have a quantum fluctuation happening just at the event horizon, you could have one of these virtual particles falling in and the other one coming out, and they can never actually re-annihilate each other. And so quantum fluctuations that are normally thought of as virtual become real. They become frozen out, in fact, cosmologically observable. So why am I telling you this story about black holes? Well, the reason is that an inflating universe actually has an event horizon too. So exponential expansion, as I said before, means that there's a doubling time for all the scales in the universe. So if we were in an inflating universe, an exponentially expanding universe, and we were playing a game of ping pong, say, and we start off across the ping pong table 2 meters apart from each other. And in a very small interval of time, 10 to the minus 38th of a second or so, an interval that I'll borrow Mike Turner's phrase, and I'll call it a jiffy. Every jiffy. Well, okay, now actually what I'm going to do is I'm going to slow it down a little bit. And instead of 10 to the minus 38th of a second, I'm going to pretend that we live in a universe that's inflating, but more leisurely. Every 1 second, the size of the universe doubles. And so we're both stationary in that universe. We're not moving, but the distance between us is growing. So in 1 second, it goes from 2 meters to 4 meters. And we can continue our game of ping pong. We just have to hit the ball a little bit harder. In the next second, it goes from 4 meters to 8 meters. We've got to hit the ball considerably harder. So let's suppose we're really good at ping pong and we can, really smash it. So we'll find that the space between us will be growing after 25 seconds or so at almost the speed of light. And if we're really, really good, you can hit a ball almost that hard. But in the next second, the space between us is growing faster than the speed of light. And there's no way you can hit a ball or anything else hard enough that it will reach your partner. In fact, you've lost causal contact with your partner. You've passed a point of no return. You've crossed an event horizon in that exponentially expanding universe where no communication is any longer possible. And will not be as long as the universe remains exponentially expanding. When the universe stops exponential expansion, slows down with a normal expansion rate, say, at some point in the distant future, we might be able to see each other again. Light might catch up, and we could resume our game 14 billion years later, say. Okay, so the point of that is that the exponentially expanding universe has an event horizon, and quantum fluctuations across that event horizon scale actually get frozen out in the early universe and become real. So this is the slide I warned you about that has equations. But the only reason I want to show you these equations are to show you how simple the equation is that tells you what the strength of the quantum fluctuations of a black hole are here. This is the Hawking temperature of a black hole. And it's just related to the Schwarzschild radius of the black hole, the event horizon scale. And the temperature of an exponentially expanding universe, known as de Sitter space, is related in almost exactly the same way to the horizon scale of the exponentially expanding universe. And the horizon scale of an exponentially expanding universe is just governed by, it's the Hubble constant during inflation. And that's directly related to the energy that's driving the expansion. So the energy scale of whatever physics it is that's driving that exponential expansion sets this horizon scale and in turn sets the strength of the quantum fluctuations. And it's very simple. It's very much independent of what this force is, what that physics is. It depends only on its energy scale. And observations do show that the primordial fluctuations that we see and infer in the cosmic microwave background have all the characteristics you would expect of quantum fluctuations. They're random. They are very well behaved statistically. They appear to have a property where they all start off in phase at the same time synchronously at the beginning of the Big Bang, as I said they must for that theory, to produce that nice series of peaks and curves. And furthermore, they have a slightly tilted spectrum, so slightly stronger at the largest scales, the ones that would have been exiting that event horizon at the earliest times, and slightly weaker at the scales that exited the horizon later times, the smaller scales in the universe. And that's a very interesting clue. That tells us that if this is the right picture of how those fluctuations were generated, then we're getting a movie, if you will, of inflation slowly rolling to an end, starting off at a higher energy and slowly tapering off to a lower energy while the cosmological scales that we can observe are exiting that event horizon. So there's actually a lot of evidence that cosmologists believe corroborate this picture of quantum fluctuations producing the inhomogeneities in the universe that lead to the growth of all structure. So maybe ultimately we are quantum fluctuations in addition to, as Carl Sagan so famously said, being stardust. But I've got to stop for a minute. So I've told you this story as though it's all beautiful and hangs together, and in some way it is. But it's also crazy. I mean, inflation is happening at energy scales that are 10 orders of magnitude higher than any that we can actually experimentally test in the largest accelerators that we humans can build on Earth. And I told you that new physics, some new force is driving that exponential expansion. I didn't tell you what it was, so we very cleverly call it the inflaton. And it's just invented out of whole cloth here. It requires new physics that we don't know anything about, really. It relies on quantum physics and strong gravity, which is something that we think we may understand, but we don't really have any direct tests of that yet. This exponential expansion process can lead to disturbing consequences. It's not necessarily inevitable in inflation that you could have an infinity of universes that are spawned in this process, but some varieties of inflation, according to some theorists, would lead to that consequence. And if, in fact, we're dealing with not just one potentially infinite universe, but an infinity of universes, does that mean that we've got the end of predictive physics, that, the ability to say why the universe is the way it is, other than just saying, well, an infinite variety of things are possible? And many of us find that quite disturbing. And does it really even help in explaining the initial conditions? I told you how it addressed the smoothness, the flatness, the relic abundance problem. But does it replace those things with conceptual issues that are really any less hard to understand? These are points that are really, really deep and are debated among theorists vigorously in our field. And yet inflation does fit beautifully. Everybody agrees with the universe that we observe. It's a compelling theory. So I view all of these things as opportunities. I think this is what makes it so fun and so interesting, is that these are big questions. We don't really know the answers, and as an experimentalist and as an observer, I don't want to put money on any of these things. What I want to do is ask, how can we test it? How can we go out and make observations that could maybe answer this question? And the key to that is to recognize that, now here's another slide showing the history of the universe. Here we've got the present-day universe and stars and galaxies running that clock back in time. We have the cosmic microwave background. All of particle physics fits in this block of time, and then we get down to early times before a microsecond or so. Inflation is depicted as this exponential expansion in the first tiny fraction of a second. If quantum fluctuations produce the initial conditions here, then it would generate these two types of waves. So the density waves would be the quantum fluctuations of whatever field it is that's actually driving inflation, the inflaton field. And that evolves to produce the acoustic waves in the primordial plasma, the pattern that we see in the cosmic microwave background temperature maps, and ultimately stars and galaxies and everything else that happens later time. But inflation, quantum fluctuations in inflation would also perturb the gravitational field. So gravity needs to be a quantum theory here in this picture, and we believe that it is. And that energy scale of inflation will just dictate the relative strength of the gravitational waves, the random fluctuations in gravity, compared to the random fluctuations that wind up in density. So the ratio of these two things will depend on the energy at which inflation happens. And these density waves have evolved throughout the 380,000 years of the early history of the universe, and we only get to see up until this point, because the universe becomes opaque at earlier times. The plasma doesn't let light free stream through, so we get a snapshot here. And we get to see these density waves after they've been processed through all of that evolution in the plasma. But the gravitational waves, if they are there, would have been passing through that early universe from very early times right up until 380,000 years and have the potential to imprint a very unique pattern on that surface of last scattering, the CMB maps that we can make. And that pattern shows up as a swirling pattern in the polarization of that earliest light. Okay, so what does it mean for light to be polarized? Well, if you think of light as an electromagnetic wave, the orientation of the electric field, which is perpendicular to the direction the light is traveling, could be like this or it could be like that. And if I tell you the light is polarized, that means you get more of one than of the other. So how does the CMB get polarized? Well, if you think of a charged particle, an electron, in that plasma 380,000 years after the Big Bang, just before it becomes neutral, just before this disappears into an atom of neutral hydrogen, it's still scattering light while it's a free charged particle, a free electron. And it's scattering the light coming in from all different directions. And if there is an acoustic oscillating density wave passing through the universe at the location of that charged particle, and in fact, in reality, there will be many such waves, all adding up at once. But let's just focus on one. If it has this orientation, then where it's denser to the left and to the right, the light coming from those denser regions might be stronger. So you have light coming in like this. The electric field of the light coming in like this will be perpendicular to that light coming in from the left and the right. The charged particle will be excited by that electric field, and it will vibrate in a plane perpendicular to that light. It'll vibrate in this plane here. And if it deflects some of those photons, particles of light, towards you, the present-day observer, who's mapping this picture now, it will deflect those so that the electric field of that light is vertical. And if the light is coming in from above and below with less intensity, then that charged particle will be shaken in this plane here, this horizontal plane, but not as strongly. And so it will deflect some of those photons with an orientation of the electric field like this, but say weaker. And in reality, this effect is very, very weak indeed, because these density fluctuations are so tiny. They're 1 part in 100,000, say, and the process isn't very efficient, so the polarization may be only 1 part in a million. For every million photons that come to you from that spot in the CMB with an orientation of the electric field like this, you might get 1,000,001 oriented like this, or vice versa, if I move this over here by half a wave and reverse all of the signs. And so that picture is what I'm showing here in the top part of the slide. If you have a radiation field coming in that has a pattern that looks like this, you would get polarization that's vertical or horizontal. This pattern of polarization, if I were to make a map of it coming from different points on the sky and depict the polarization orientations by these little headless vectors here, vertical or horizontal, corresponding to this pattern made by that density wave passing through the early universe. So I can reorient that pattern any way I want, but that pattern is a very specific geometric pattern. In particular, the polarization vectors there are not aligned plus or minus 45 degrees to the direction of that wave. And if I wanted to get a pattern that looks like this, plus or minus 45 degrees, I would need to introduce another direction in the problem. There's no way I can do it with a density wave, because there's no way to select plus or minus 45 degrees when the problem has this symmetry. If I were to flip it around, it would look symmetric. And so if I want to break that symmetry, I need to introduce a new direction in the problem, and a gravitational wave can do that, because a gravitational wave is a stretching of space-time where a wave that is passing through the universe like this will cause transverse compression and expansion. The compression is depicted like this as brighter radiation, hotter radiation. The expansion is depicted like that, colder radiation. And it's possible to make this orientation such that it lines up at an angle with the direction that that wave is passing. And so I can get a pattern that looks like this. The key here is that there's no way I can get these patterns, which are so-called Bmode polarization patterns, from density waves. They just don't get produced. So I could reorient these patterns any direction I want on the sky. Any direction is as good as any other. And if I add up a bunch of these E-mode patterns, I get patterns that can look radial or tangential, but don't have any swirling to them. To get patterns that have curl or swirling to them, I need to have some of this B-mode polarization. That indicates there's new physics going on. And so this is what we're going to be looking for with our telescopes, is patterns that have this swirling pattern in the microwave radiation. Okay, so back to a power spectrum plot now. I showed you the power spectrum plot before of the temperature, which is up here, now at the very top of the plot, which shows the strength of those density fluctuations as a function of angular scale here. And the point I guess I want to make with this plot is that these acoustic oscillations in the temperature spectrum are the same ones that drive the E-mode polarization pattern here. You see the same spacings of peaks, but just different relative heights of the peaks, because it's the same density fluctuations, the same acoustic oscillations that are making those E-mode patterns, but they're much, much fainter. They're down by, this is a logarithmic scale, so down by a factor of 100 at least. Instead of talking about tens of microkelvin, we're talking about a few microkelvin at most. So the swirling patterns that come from inflationary gravitational waves peak at large angular scales, to this side of the plot, degree angular scales, and they're much, much fainter still. And how faint they are depends on that ratio, this all-important ratio, which we're going to be calling R for ratio of gravitational waves to density fluctuations in the early universe through the rest of the talk. And so this spectrum, which is speculative, could be higher or lower depending on the value of R, the value of the gravitational waves in the early universe. Now you can also generate B-mode polarization patterns from the distortions of the not swirling part, the E-mode part of the polarization pattern, that come from other gravitational effects that happen at much, much later times in the universe's evolution. The so-called weak lensing, or the deflection of light, very subtle effect by collapsed mass in the universe. As we go from very high redshift to the present day, deflects all the lines of sight that we see by a very small amount, just a few arc minutes on average. But that's enough to distort a pattern that has no swirling into a pattern that has a little bit of swirling. And so that's what you see here. You see a smooshed out, smooth, and much fainter copy of this E-mode pattern here in the distortions that come from the lensing B-modes. So these are two different physical effects that can take a simple picture where you have no swirling in the polarization of the CMB and add swirl. You have inflationary gravitational waves here at the large scales, and you have gravitational lensing at smaller scales. So there are other more prosaic ways of getting B-mode polarization patterns on the sky that are very important and arise from different physics that are introducing a new direction into the problem. And in this case, I'm talking about primarily the galactic magnetic field can introduce a new direction to the problem and orient radiation that comes from our own galaxy in a way that can have a swirling pattern. You can get both E modes and B modes from radiation that comes from our galaxy, whether it's low-frequency radiation, radio emission, that comes from charged particles spiraling in galactic magnetic fields, or whether it's emission from galactic dust particles that dominate at higher frequencies. And here, the dust particles can be oriented by galactic magnetic fields, and they can emit preferentially polarized light. So the key thing about these galactic emission mechanisms is that they have a different frequency spectrum than the CMB, different color, effectively. And so we can use observations at different frequencies to disentangle them from the CMB. And up until quite recently, we had no high-frequency maps of the polarization in the clean regions of sky. We did have low-frequency maps of polarization, and so we do have some information on the strength of the radio emission. But we had virtually no information on the dust until just last year when the Planck satellite produced such polarized dust maps. Okay, you've been very patient, sitting through many plots up until now. So now I'm going to show you how we actually do these measurements. For me and for my group, central to that story is you go to the South Pole, and you get there by flying first to New Zealand, and then the U.S. Antarctic Program and the National Science Foundation sponsor your travel from Christchurch, New Zealand, to a U.S. station on the coast of Antarctica called McMurdo. And from there you fly to the Amundsen-Scott South Pole Station here, another 800 miles inland. So when you're on the coast of Antarctica, you might be so fortunate as to encounter all of the iconic flora and fauna. This is an Adelie penguin. And it's fun, but you're only there for a day or two because you've got to get to the South Pole and get to work. And when you get there, it's pretty sobering. It's completely sterile. So this is what it looks like when you look away from the station. Then you turn around and you see your telescope coming out the back of an airplane. And maybe you'll see your colleagues coming out the front of the same airplane. We all take the same airplanes down to the South Pole. And this is what it looks like. So winter operations at the South Pole are something that we've been doing now for over 20 years. And we started from very challenging, humble beginnings. I told you it can be minus 100 degrees down there outside in the wintertime. And when we first started to try to make microwave telescopes that exploited those extraordinary conditions, we did the natural thing and we put them outside. This person had the job of hauling liquid helium up to cool the detectors in this telescope that's housed in this apparatus. And I can tell you that was not an easy job. I can tell you that because that was actually me. I had the job of running that first telescope. And it was a good learning experience on how not to do such experiments efficiently. We succeeded in making some useful measurements, but mostly we succeeded in learning how to design the next generations of telescopes. We've now had almost 10 generations of these telescopes operating down there successfully. Excuse me. So fast forwarding to a telescope that's designed much differently. Here you can see there's this big insulated sleeve, and to work on this telescope, you work on it from inside in a shirt sleeve environment. This telescope here has 13 receivers that are pointed up at a small patch of sky and integrated for a long time on that patch of sky, measuring the polarization of the CMB for the very first time. In 2002, the E-mode polarization pattern was detected at the South Pole with this instrument, and I was very fortunate to work on this project. It was my PhD thesis. This was John Karlstrom's telescope. He's at the University of Chicago. we made this map, and this map has polarization vectors that don't swirl, effectively. They are E-mode, so they are mostly a gradient type. So no swirling pattern here, but it's an extremely faint pattern. It's measured in a few microkelvin at most in these vectors. And this was big news, but of course, we were mostly motivated in this field by the promise of studying new physics in the swirling pattern, the B-mode polarization. And I told you before, that's much, much fainter, another 100 times fainter. So instead of measuring in microkelvin, now we're measuring in nanokelvin, in billionths of a degree. And so this shows a power spectrum, again, of the B-mode polarization. And these symbols indicate that it hadn't been detected for the 10 years after that initial detection of E-mode polarization. For a whole decade, we just pushed down upper limits, depicted by these symbols here, pushing down to ever greater sensitivity, measured now in fractions of a microkelvin here, pushing down into the nanokelvin territory, but trying hard to push into this region where we could, these dotted lines here depict the B modes from inflationary gravitational waves at different hypothetical strengths. And we're just starting at the end of this sequence to touch the theory lines at the highest conceivable energies. So how do we get there? How do we do these measurements? These are degree angular scales. So these are big patterns on the sky. And to resolve them, you don't need a very big telescope. In fact, we use refracting telescopes that are a lot like Galileo's original telescope. It's a 2-lens refractor, but the whole telescope has to be cooled to 4 degrees above absolute zero. It needs to be that cold because we need it to be exquisitely stable and sensitive to this extraordinarily faint microwave radiation. In fact, the focal plane here has some amazing technology in it, detectors that are cooled to only a 1/4 of a degree above absolute zero, and they're superconducting. And each of those detectors is operating at the quantum limit of how sensitive they can be. So the only way of making more sensitive maps with them is by either waiting longer and waiting for more photons to hit your telescope, or by building a telescope with more detectors. And that's what we've been doing over that period of the last 10 years, and in recent years especially. We've gone from telescopes that have names like BICEP 1, BICEP 2, Keck array, now BICEP 3, that have had growing numbers of detectors. So for people who have digital cameras that have megapixels, these may not be very impressive numbers, but we've gotten now into the kilopixel regime with these telescopes, and we're very proud of ourselves, because this requires extraordinary custom technology. The detectors are superconducting. I won't take the time to explain the technology, but I'll be very glad to talk at length if you have questions on it, because it's really cool, and it's a big focus of what the people in my group actually do, is develop technology that's quite custom, that patterns superconducting detectors on silicon wafers and allows us now to mass produce hundreds or even thousands of these detectors. This is a detector island that's actually doing the work of detecting that very faint microwave radiation in one polarization. The other polarization is detected over here for just 1 pixel in this camera that we're building. Read out with superconducting electronics. Here's a graduate student at the South Pole in a clean room that we've erected there, and a fun sign that was put on the outside of it. Please do not feed the graduate students, it says. So this just gives you a flavor of what it's like to work at the South Pole. It's actually pretty good, as you can see, that we've got good crane support. We can do things on a reasonable scale. These telescopes are really a good manageable scale project for a few dozen people to put together. And then when we finish putting it together, what the telescopes do is very boring. They just go back and forth, back and forth, back and forth on the same patch of sky as it tracks around 24 hours a day. And it does that for the better part of the year. So this is what it looks like at the beginning of the year before the sun goes down. And if things go well, the winter over telescope operator has gotten rid of all the summer crew, and he can just enjoy the sunset, kick back. And then we have a long polar night, and it's absolutely spectacularly beautiful, except when it's stormy and not. And for months and years, here 3 years of observing are shown across the bottom of this plot with the BICEP 2 telescope. We just collect more photons, and the map gets more and more sensitive. This is a depiction of the polarization maps noise formed by taking half our data and another half of our data and subtracting them, so removing the signal and just showing the uncertainty. The noise in the measurement here gets smaller and smaller as we collect more and more photons over 3 years. And the signal here, the full signal is shown in the polarization maps, is emerging above the noise. So exquisitely faint signals. This color scale is a microkelvin. And if we make a polarization vector map of that, it looks something like this. So this is the map made over 3 years with the BICEP 2 telescope. And the scale of this is a little bit more than 1 microkelvin, 1/1,000,000th of a degree for these polarization vectors. And this is mostly an E-mode pattern. If I take out the E-modes and show you only the B-mode part of that pattern, it looks like that. Much, much, much fainter. But this is still measured with very high signal to noise after 3 years. And so if I blow this up and show you what that B-mode pattern looks like, it looks like this. If I color it in to draw your attention to the clockwise and counterclockwise swirls in that B-mode pattern, it looks like this. And after 3 years of observation and 4 years of analyzing this data very carefully, our team looked at every which way that they could and determined that this pattern was real. It was on the sky, and that this B-mode pattern was actually stronger on degree angular scales than anyone had expected to see. And so the key question is, what is it? So the B-mode results that our team reported in March of 2014 are shown here now in an angular power spectrum. These are the BICEP 2 points that come from that map I just showed you. And the black points are an excellent fit to the B-modes expected from the lensing signal up here, securely predicted, and this curve here, which is inflationary gravitational waves that are a ratio of 0.2. But we know that that there are galactic foregrounds in the sky too. And so understanding whether these B-modes were galactic foregrounds coming from our own galaxy or coming from inflationary gravitational waves from the early universe is really the key issue with knowing what to make of these B-mode measurements. And when BICEP 2 made its measurements, we had only one frequency, only one color of light that we had gone to anything like this level of precision with. So we were able to constrain with other maps that were available the radio emission that was contributing to the B-modes. But for the dust emission from our galaxy, we didn't have high-frequency polarized maps. We only had models that had been in common use in the field, and those models predicted much fainter B-mode radiation on average as being likely at these angular scales. And so the interpretation of this big excess B-mode signal as evidence for gravitational waves relied heavily on those models of dust emission, which were calibrated on regions where the dust is brighter, and we were observing in the faintest regions of the sky. So that turned out to be naive. The models did a good job of matching the data that they were designed to fit, and did a poor job of extrapolating to the regions of sky where the radiation was much fainter. So to show this another way, I talked about parameter degeneracy plots. Okay, so this is a parameter constraint plot with ellipses like the one that you saw before. The B-modes that we observed could come from inflationary gravitational waves, and that would push them out on this axis here, measuring R, or they could come from dust. And with the data that we had back in 2014, we have this axis of degeneracy. We can't really tell the difference very well between dust and gravitational waves. Now, the data did favor this point here, but it only ruled out this point here at 1 in 10 odds. But the dust models that existed at that time, that were in common use, predicted levels of dust that were down here. And so if that were right, that would line up well with what the data had been saying, and that would imply that there has to be a good fraction of that signal, most of it in fact, coming from inflationary gravitational waves. So the relative likelihood of that parameter R on this plot down here would be like the colored curves under these different models. But these models were uncertain. And they ultimately needed to be confronted with actual measurements. And when that started to happen, when the Planck satellite came out with measurements of the dust, they weren't high enough precision to say exactly what the dust was like in our region of the sky, but they were precise enough to say that the models themselves are suspect. We shouldn't rely on the models. We need better data. And so that came in part from combining the Planck maps that were made with this satellite at 9 different frequencies, 7 of them polarized here, with our own data set in a joint analysis that we embarked on last year and that we published early this year. So I'm getting close to bringing you up to the present day in these last few slides. So you can see at these different frequencies, at the low frequencies here, the radio emission from the galaxy dominates. And at the higher frequencies in this bottom row, dust gets brighter and brighter. These two maps don't have polarization information, but this map here at 353 gigahertz did have polarization information. We were observing here, where the Planck maps are mostly noise. But there was enough information in the cross-correlation of the Planck maps. If we cut out that small bit of the Planck maps at this high frequency and compare it to the BICEP 2 Keck maps, which have very low noise, we see something that looks like this. This is dominated by very strong noise and dust. And here you can see how much brighter the E modes are compared to the B modes in our BICEP 2 maps. So I'm going to put all these on color stretches where we can actually compare the patterns. And by eye, you still can't say whether the patterns in the high frequency maps from Planck are similar or different enough to the patterns measured in the BICEP 2 map that there's enough in common here to indicate dust entering into both of these maps. You have to do a statistical analysis. And when you do that, the parameter constraint plot that showed a strong ellipse here before collapses that ellipse to a point that looks like this. And that point indicates that, yes, the dust is bright in that field, bright enough that it must explain at least 40% of the full signal. And it could explain all of it. So if we look down here, the evidence for this parameter R now is that there's no significant evidence that this parameter isn't 0. It peaks here, but it doesn't rule that point out. It does set an upper limit on how strong these gravitational waves can be, no more than about 12% of the strength of the density fluctuations in the early universe. So this is good. This is definitely progress. But we need much better data if we're going to disentangle these signals and go further. So we need to separate out the components that are entering into our B-mode maps by having very precise data at multiple different frequencies. And the start on this you can see here now we've used the Planck data at high frequencies to separate out the dust contribution shown in green and the contribution that has the right color for CMB in black. I take the dust away. We can see that the CMB points in black are compatible with a variety of values of R, including R equals 0, no gravitational waves, but also R equals 0.05 or a little bit higher. So we need higher precision data to separate out these components, separate out the galactic foregrounds, and it's coming very fast. And the other thing that's coming is measurements from telescopes like this, the South Pole Telescope, Polar Bear. These are much larger telescopes than ours that are able to measure small angular scales and map out the lensing signal, which is actually very interesting on its own because it tells us all about all of the integrated mass between us and the very edge of the universe, redshift of 1,000. So there's a lot of really rich physics to be done just in studying that signal intrinsically. But it's also very helpful because we want to remove that contribution from the degree angular scales where we're interested in probing as deeply as we can for gravitational waves. And that's coming. So just to give you a flavor of this, now this is the last parameter constraint plot I'm going to show you. This is showing now on this axis the strength of R. So this is the strength of the inflationary gravitational waves. This is telling us the energy scale of inflation on this axis. And this is showing us the tilt, how red the spectrum of primordial fluctuations is. And these two things are the two primary things that characterize different models of inflation, different pictures that theorists might construct for how inflation evolves and what energy it operates at. And theorists can make plots where they have all different points on this plane labeled with different names and different shapes, different functional forms for the effective potential of the inflaton. But the key thing here is that the data are zeroing in on this very rapidly, are constraining this plot, cutting down on the parameter space. So with no B modes, just a year ago, what we had was this red orange contour here, and we add in the B modes, and it's starting to shrink significantly. And that shrinkage, the uncertainty on this parameter R, is going to be continuing to be reduced a lot in the next few years. And that's what's exciting to me, because so many of these models of inflation that live in this region of parameter space will be tested directly by the data, confronted, and either we will see the data circle around one of these models and confirm that, yes, we have inflationary gravitational waves at this strength, and it matches up this idea for how inflation happened, or it will exclude a bunch of models, and that's equally exciting to an experimentalist like me, proving that the universe didn't happen that way, and we have to keep looking. So what's driving this are multi-frequency maps. Here I show 3 different color maps from our own telescopes this year, which haven't been published yet, but which are going much, much deeper than anything that you've seen before. I'm showing the high-resolution data that's going to let us remove that lensing signal. And I'm showing here just the uncertainty on this parameter r and how it's shrinking as a function of time. And this is just over the last couple of years. It's shrunk almost, it's almost cut in half. And over the next 3 years after that, it's going to shrink a lot more dramatically. And that's cool because the region of parameter space that we're probing by measuring r to less than 1% accuracy is the region of inflationary theories that correspond to inflation happening at so-called GUT scales, Grand Unified Theory Scales, GUT. And it's a very theoretically compelling region of parameter space. And if we show that inflation didn't happen in that region of parameter space, it will really restrict our ideas for how this theory, if it's correct, could have actually worked. So to show you some pictures of people now, finally, on our team who are making these apparatus happen. These are 2 people from Stanford, collaborators working on the focal plane of the BICEP 3 telescope that Sam R. Winterover is operating at the South Pole. These people, Abby and Jamie here, are working on a focal plane of the Keck array. And so again, I said we can expect the uncertainty on R to be halved by the end of this year with the data that we're taking. And there are lots of other telescopes that are operating in this field, some of them very large. And the cool thing is that the progress is so rapid, and there's such a diversity of approaches, sizes of telescopes, complementary approaches, different frequencies, different scan strategies, and all of this data being used together is really going to help us get a rich bounty out of these maps that we're making of the first light in the universe. So it's an exciting time to be doing cosmology, and I just want to ask you all to stay tuned.
Now time for the question and answer period, and we're running a little long, and I want to make sure everyone has a chance to enjoy the beautiful clear skies, so I'm going to keep it a little short, but you're welcome to stick around and come up afterwards. Yes, ma'am, right up front.
What's the process of making the detectors for the telescopes?
The process of making the detectors for the telescopes is it's a great question. It's a long and arduous one. Let's see. I'll tell you what, I'll go back to the plot with people on it. So I showed you a slide that showed a close-up of the detectors before. So these are what the detectors look like after they've been integrated into the focal plane of the telescope, behind the lenses of the telescope. To make each one of these tiles, they're patterned on silicon, and the process is a lot like the same way that microprocessors are made on silicon wafers. Except it's done in a custom shop at a NASA facility called Jet Propulsion Laboratory in California. And instead of making semiconductors on that silicon wafer, we make superconductors. And they work because the temperatures here are so low, just a fraction of a degree above absolute zero. And by using superconductors, we're able to make these detectors exquisitely sensitive to very faint microwave radiation. It doesn't take very much energy at all to excite those detectors because there's essentially no resistance in the detectors that we're using. So if you want a more detailed answer, you can come up afterwards and I can give you about an hour-long explanation of all the different steps in processing these wafers. We're trying right now very hard to produce the set of wafers that we need to take to South Pole next month. And so there are a lot of students who are working on that right now in the clean room.
Yes, ma'am. Given the expansion and contraction factor, what is your personal inference before the Big Bang? Was there a probable expansion phase that resulted in the contraction that gave rise to the Big Bang?
I'm just going to repeat that because I'm not sure our microphones picked it up. What came before the Big Bang? I think is a good way of summarizing it.
Yeah, it is.
Oh, I had my microphone off. Why don't you repeat the question?
Sure. Okay. The question was essentially what came before the Big Bang? Was there a contraction phase before the Big Bang? And to answer that question, I guess first I've got to say there's a bit of confusion about what we actually mean by the Big Bang itself. And what I mean, and what I think a lot of us mean by the Big Bang, is the phase of hot early expansion of the universe that's part of the standard model history. So we know that the universe had a hot, dense early beginning and expanded from that hot, dense early state. And I think that's pretty secure. So inflation might have happened before that standard Big Bang picture. And that would have been an explanation for the initial conditions of the Big Bang, as we usually describe it, where this exponential expansion sets the initial conditions. And what happens in the early phases of inflation or before inflation is very speculative because we don't have clear testable hypotheses that we can go out and falsify for most of those theories.
Given the expansion contraction notion, there could have been a series of contractions.
Yeah, so there are some alternative ideas for theories that don't involve inflation, it's exponential expansion, that involve a much slower expansion or a contraction phase that could have set up the initial conditions. And those are not as well developed as inflation. They're not as popular as theories, but they're still out there and they're viable, and people debate them and argue about them. And I think that that's what makes the field really exciting. But I want to distinguish that from the standard Big Bang history, because we know from all the evidence that we have that the standard model of cosmology takes us back to a small fraction of a second. And the universe has been expanding for the last 14 billion years, 13.7 billion years, starting from a very hot, dense early beginning. So the question is what happened before that, as you said.
Yeah.
Okay.
Another just point of interest, Howard was in Antarctica in 1959 for 15 months.
Wow. I would love to talk to you after this. That is remarkable. Wow. Well, it's an honor to meet you.
All right, I have one final question, and that comes from our overflow room, actually. And the question that they wanted me to convey is, you mentioned future missions, the ground-based telescopes, balloon-based, any future space missions to study the CMB?
So we hope so, is the short answer. We have a number of future space missions that are being studied right now. So there's a Japanese mission called Lightbird. There's a European mission that's under study. There are a couple of ideas for missions that might be sponsored by NASA here in the US. And they all have slightly different approaches. And I can't say that any one of them has yet been approved and we're certain that it's going to go forward. But they have, each of them have a different, unique way of exploiting being in space, being above the atmosphere, being able to map the whole sky, which complements what we're doing from the ground. But the story that I'm telling you about going very, very deep in a small patch of sky to search for these inflationary gravitational waves to go after this parameter r that would characterize their amplitude if they're there, or set the best possible upper limits on that parameter if we don't detect positive evidence of them. I'm personally of the opinion that we can go very, very far on that just from the ground. But the CMB itself is so rich scientifically, and there's so much yet to be done to measure its polarization on large scales across the whole sky, or to map out the distortions of its almost perfect but not quite perfect blackbody spectrum, that there should certainly be one or more space missions over the next decade that can really get that rich science out of it. It's been the primary tool that's driven cosmology for the last couple of decades with precision measurements, and I think it's going to continue to give.
All right. I don't know about all of you, but I feel like my mind has been stretched almost as much as the universe. With that, we're going to wrap up our